one more eminent speaker, Dr. Dinesh Balasubramanian. He is a Chief Research Fellow and full professor at Lithuanian Maritime Academy, Lithuania. He completed his bachelor's in mechanical engineering from Kongu Engineering College, Coimbatore, and post-graduation from Madras Institute of Technology and PhD from Anna University, Chennai. He completed his postdoctoral research fellow PhD from PDF from Thailand as well. He was recognized as world top 2% scientist in 2021, 22, 23, 24 under energy research area. To his credit, he has guided 4 scholars as well. Now he is handling the projects worth of 35 lakhs, including one international bilateral collaboration project between India and Taiwan. He published 9 patents, 130 plus Scopus indexed papers, with Google Scholar citations are around 6,219, with H index 45 and I10 index 95. A wonderful, eminent research personality, Dr. Dinesh Balasubramanian. Thank you, sir, for accepting our request, and over to you, sir.
Okay, sir, whether the screen is visible?
Yes, sir, yes.
Whether am I audible?
Yes, please proceed, sir.
Okay, sir. Can you see the slides are keeping changing?
Yes, sir. Yes.
Okay, sir. Okay. So thank you. I just welcome you all to this particular session, and I will like to thank the organizer for giving me such an interesting opportunity where I can present a lecture on my expertise area, and we will have a brief discussion about AI enhanced prevention, particularly on thermal runaway in lithium-ion batteries, focusing more towards safety and innovation in advanced mechanical system. So for next 1 hour, I will give you the basics about batteries, the thermal runaway issues, and make you to walk through the different techniques that we currently follow and how AI enhanced technique is used to prevent this thermal runaway. And the overall presentation is scheduled in this particular fashion, where we will try to start with the battery fire concern, and I will talk in detail about the lithium-ion batteries in general, and what is thermal runaway, how it is originated, or how it is initiated, and how it is allowed to get progress. So that is what my main focus lies on. And next, we will have a discussion about the standards and the regulation challenges. What are the various standards and the regulation challenges that currently we have? And next, I will try to talk about certain research gaps, and I will give you a few case studies focusing on the heat transfers and the predictive theory of thermal runaway of LIB stands for lithium-ion batteries, and few projects was that we are currently working on related to the area. So this is what the entire session is focused on. So starting with the thermal runaway, as this image represent, it is not that the entire battery would completely get fired. So it is that one particular cell might face an issue. Because of that, the flame is getting propagated to the nearby cells, and after a short time scale, the entire battery pack is allowed to get fired. So we need to critically understand which particular cell is allowed to get damage, and if we are able to suppress or handle that particular cell, then it won't be a big issue where we can entirely safeguard the entire battery pack. So that is what is the glimpse and idea about this particular GIF image. And moving on to the battery fire concern, this give you a slight idea about why this particular topic is more interested as of now, or what is the need for this particular topic in this particular scenario. So in most often cases, I would like to start the presentation with the related news, so we can try to understand the importance of this particular topic. So it would be easy for all the participants to get connected with it. So here is one interesting news that talks about five get injured and three critically ill because of lithium fire battery issue. So this is one major point that we need to understand. That is because of the battery fire issue, we are facing critical illness as of now. And next is that the Jaguar has a recall close to 6,400 vehicles, particularly an electric SUV, because of one particular concern is the battery fire. So I hope you are all aware about Jaguar, which is a leading automotive manufacturer, but still they face issues related with battery fire. And next important part related to is that you can see few images which represent how the battery fire would happen. Initially, it starts with a smoke formation. As time progresses, the flame is allowed to get propagated to a huge mass. And the issue is that to suppress this entire vehicle battery fire, we need to spill lot and lots of water. So firefighters also face critical issue in suppressing the battery fire. Then lithium-ion battery fires from electric cars and bikes are on rise and or firefighters ready for it. So this is also one major criteria because when dealing with battery fires, the firefighters also need to be get trained related to this concern. So if you see in detail, one term that is keep on repeating in all the news that is available online is the battery fire. So this battery fire is becoming a major concern in this 2025 and even maybe for next couple of years. So people are facing a lot more issue related to this battery fire, and I will make you understand what does this battery fire talks about and how it can be effectively handled. And when you look more detail into this particular slide, which give you the numbers of cells that are produced. So as of now, for this particular slide, I have considered a cylindrical cell of close to triple A size battery based on the statistical data collected in 2018. So let us assume by 2018, close to 8.2 billion cells are produced, and among that, these 8.2 cells are allowed to use in your vehicle. In that, it has been roughly calculated less than 1% might result in a failure issue. And even if less than 1% is allowed to get failed, only 0.00002 percentage might result in a safety event. So when you look at this number, the 0.00002 is very minimal. So it is not a major issue. But when you just try to break down it into numbers, this 8.2 billion is close to 820 crores as of Indian concern, and in that 1% is close to 8.2 crores, and 0.00 and 002, maybe a zero extra, would be close to 16.4 or 1.64 lakhs. So among this entire cells, this 1.64 or 16.4, maybe I have not worked with the numbers exactly. If you try to look into detail, either both the cases are enormously high, that might result in a safety event. So we doesn't know where this 16.4 lakh cells is present in the entire electric vehicle that has been sold out. So who is going to be that lucky winner having that safety concern battery is the primary concern now. So each lithium ion cell is a reserve lottery ticket, and this 0.00002 percentage cell might face an safety concern. So that is what here we need to understand. So it is not that entire cells present inside your vehicle would result in a thermal runaway issue. Among that, only a very minimal percentage might face a thermal runaway issue. So that what is the primary takeaway from this particular slide. So the safety event in lithium-ion cells batteries are incredibly rare, but their severity mandates deliberate strategy to deal with possible occurrence of thermal runaway. So that is the key point over here. And before moving into this in detail, we'll try to understand the basic working of lithium-ion battery. So you can yourself try to understand why does this issue happens. So we'll start with the great inventors initially, and I hope you are all aware about who's there in this particular slide. And this is Alexander Volta, who invented the cell in the earlier time scale. And here is the invented cell path with make use of the primary materials to work as an cell. And I hope you might have come across these names in intranets. So this is Akira Yoshino, John Goodenough, and Whittingham. So these key personalities or the Nobel Prize winner in chemistry stream under 2019 year. So they have been provided the Nobel Prize for their invention of lithium-ion batteries. So when you look more detail into these three personalities, all of them are not in the same era. All of them are not in the same region. All of them are not working in the same workspace. So all three are entirely from a different zone, entirely from different perspectives, and they have been awarded the Nobel Prize for their invention towards the progress on lithium-ion battery working in an effective way. And talking about lithium, in the entire periodic table, lithium is standing close on the top of the periodic table, and lithium is an ancient element that are created during the first minutes of Big Bang theory. So that's what this talks about, and it just stays close to the hydrogen, which stays there as an lightest element. So that is the reason why all automotive manufacturers are more interested towards the lithium-ion battery. And when you look more detail into the lithium-ion battery working, so lithium is wound with 3 electrons on the outermost orbit, and in that the 1 electron stays on the outermost circuit, and this electron has the tendency to stay or lose away its position. So thereby it would be converted into a lithium ion. So lithium is having a higher tendency to lose an electron, and this electron is what our primary interest of collecting this electron and allowing it to pass through and wire will produce electricity. So lithium atom is available with 3 electrons, and it has the higher tendency to lose an electron. As it is highly unstable, lithium is always tried to get placed inside an metal oxide. So here you can see this is the lithium ion, and this lithium ion is placed inside an metal oxide. So that is how the lithium can be made much more stable. And in most often cases, I'll try to mention it in a different perspective, so it would be clear for you to understand it. Before that, we will try to understand the history of lithium-ion battery. So talking about history of lithium-ion battery, that is not a new technology that is getting popularly used as of now in 2020s or later stage. It started in the early time scale of 1970, which is really a lot more time from as of now. So it started with the Whittingham discovery. So Whittingham tried to deal with an anodic metallic lithium in the initial state. So as I said, lithium is highly reactive and it has a higher tendency to lose an electron. If the electron is allowed to get loose from this configuration, you need to allow the electron to make the longer distance and try to move to the opposite direction. So in this case, he tried to deal with cathode. In the cathode, he deal with the titanium disulfate as the primary source material. And even at that particular point of time, that is in 1970, the researcher were facing issue with the battery fire. So this what talks about the battery fire in the initial stage, where it forms a whisker formation from the anode to cathode side. So once a whisker means and water solid layers that is produced because of this electrochemical reaction, and this forms a connection between the anode and cathode side, and it results in short circuiting. As an end of it, the battery fire issue was initiated. So battery fire issue is not a new one that the entire research community is facing as of now in 2020 or later stage. It is the issue that the researchers are fighting for past 40 to 50 years from the earlier research progress of the lithium-ion battery working. And then comes the good enough discovery. So instead of making use of the titanium disulfate, that is metal oxide instead of metal sulfate, he tried to deal with an metal oxide. So he just replaced this titanium disulfate with cobalt oxide, and in the another side he dealt with the primary lithium as a base working, and it resulted in a higher voltage level, which is more or less close to the same one as of now. And good enough started to use cobalt oxide in the lithium battery cathode. This almost doubles the battery potential and made it much more powerful. So that is what a great progress from Whittingham discovery to good enough discovery, where he just changed the cathode material in an effective way. And here comes the hero of the current lithium-ion battery evolution. So that is Akira Yoshino. So he is an industrial expert. What he did is he just tried to incorporate a petroleum coke. It has the same lithium-ion battery technology, which make use of lithium and a cobalt oxide. But he tried to introduce the petroleum coke into this existing chemistry structure. So this petroleum coke later get evolved as the graphite layer in 2020 and the later stage. So hereby, the Akira Yoshino plays a key role in the existing chemistry model of Whittingham and Goodenough. Akira Yoshino used Goodenough's lithium cobalt oxide in the cathode, and in the anode, he used a carbon material, particularly petroleum coke, which can also intercalate lithium ions. So he tried to intercalate the lithium ions into it to make it much more stable. So that is what a critical breakthrough that happened in lithium-ion battery. And after that, the lithium-ion battery was a great success. So this lithium-ion battery would be in general as highly reactive, but when it is able to lose an electron, it can be effectively deal with deal with a stable part. So that is the key over here. And among the entire voltage level plot, lithium is having the higher voltage potential, so it can be effectively used in the batteries. So the only disadvantage is lithium is highly reactive, so you cannot place it as it is. You can try to pack it inside a metal oxide. So that is what the key fact over here. So if you are able to separate the lithium from your metal or your existing source, so it would be easy for you to understand the basic working. So let me try to put it in a different way. Let us assume, as we are more often faculties, we try to pick our students for any excursion, and we have one mischievous boy. Let us assume that mischievous boy is the lithium, and the faculty is the metal oxide. So whenever the lithium is close to the metal oxide, the metal oxide is the equivalent of faculty and the lithium is the equivalent of the student. Whenever the lithium is close to the metal oxide, the lithium will be much more obedient. But when you are trying to pull this lithium far away from the structure of the metal oxide, this lithium will be highly reactive. The term highly reactive means it will get breakdown into lithium ion and an electron. So let us assume they are moving for an excursion and they are returning back to their rest place. And there are two places. One is the dormitory for students and another one is the guest house for the faculty. Once the day is allowed to get end, what actually happens is the faculty is moving to his guest house and the students are moving to their dormitory. And the interesting part is we have a wall nearby, and nearby the wall there is a very big swimming pool. Faculty says that you are not supposed to go to the swimming pool, so try to be in your room and we can go for another place in the next day morning. But what this mischievous student will try to do is he will always try to disobey the faculty and try to jump over to the swimming pool once the day is set and faculty move to his room. So that is what is happening over here. So once the faculty is away, once the lithium is away from the metal oxide, it is getting converted into lithium ion and an electron. And here we can take a liberty that the electron is very a fat guy. Assume the electron is a bit fat guy and lithium ion is a thin guy. So we have small gaps in between where lithium ion can pierce to the horizontal direction and move to the swimming pool. But as the electron is bit fat, when it's trying to move to the horizontal direction, it is not foremost sufficient to move in the horizontal direction. So electron takes the longest path to reach to the swimming pool. So once they try to play for a short time and they return back to their original position. So this swimming pool is nothing but the graphite. The wall in between is the separator, and this is your metal oxide, a lithium metal oxide. So this is how you need to understand the basic working of an lithium-ion battery working. So the lithium is highly reactive. It is placed inside an metal oxide. When you are able to pierce the lithium from it, it is getting breakdown into two components. One is lithium ion and next one is the electron. The lithium ion travels an horizontal direction and the electron takes the longest path to reach the opposite side. And once the day is set or once after a short time scale, they will get back to their original position and get it settled. So this is the charging and discharging of the lithium-ion battery. So here you can see clearly whatever I have said. The green color is the metal oxide and the red color in between is the lithium. So this is the cathode plate. So where the plates are positively charged. So this will try to pull the lithium outside. So once the lithium is pulled outside, it will be getting converted into lithium ion and electron. As the plates are positively charged, the electron would get stick to this plate. And as similar, the graphite is nothing but a swimming pool. And we have another copper collector plate over here. And this plate would be negatively charged. As lithium is positively charged, it gets attracted towards the negative plate over here. So the lithium ion travels in the horizontal direction to the graphite area, and the electron need to take a longest path to reach to the swimming pool. So this what talks about the charging part, and the vice versa case is the discharging part. In case of discharging part, they will get back to their original position. So this is how a simplified lithium-ion battery works. And the interesting part is that we have a greater invention known as solid electrolyte interface. So the first time when the lithium moves in the horizontal direction, what actually happens is it forms a solid layer on the outer side of your battery. So that, okay, I'll get back to this. For the first time, when lithium moves in the horizontal direction, it forms a barrier on the outer side of the electrolyte. So this is the barrier. And this is the graphite or the swimming pool based on our analogy. So either you can take it as graphite or swimming pool. So for the first time, lithium travels through the wall and get back to the swimming pool area. This act as a barrier. It reacts with the electrolyte and forms a barrier, and this also plays an additional repellent for the movement of electron in the horizontal direction. So our primary objective is that always electron need to take the longest path and the ion need to take the shortest path to travel from one side to other side. So in between you have the separator and the electrolyte section in between. So this is the beauty of the lithium-ion battery working. And what are the issues related with the battery? So rechargeable lithium-ion batteries are regarded the most suitable energy storage device. For lithium-ion batteries, the performance is closely related with the temperature. So here, the temperature plays a primary role. If the temperature is higher, the battery would react it in a different perspective. And if the temperature is lower, the battery would react in a different perspective. So here, the temperature is the key component. And thermal runaway is a phenomenon that can lead to destructive consequences, such as rapid temperature rise or gas generation or even battery explosion as the process of temperature increase is accelerated. To reduce the potential risk of thermal runaway, various safety mechanisms are introduced. Either it can be safety vent, thermal fuse, automatic reset device, shutdown separator, chemical shuttles, coatings, heat retardant electrolytes, and electrodes. So all these are the primary research area that lot more researchers are working worldwide. All these topics are interested PhD research topics where either mechanical, chemical, electrical engineers can work on these areas to understand how the heat is generated within the cell and how effectively it can be suppressed. So I'll give you a few examples about these topics. So this is a safety vent that is present inside your a battery. So all batteries have this small vent. You can see the small vent over here. We have an electrochemical process where the electron moves from one side to other side. The lithium ion moves from one side to other side, and we have the molten or the paste-like structure of electrolyte in between. So as the heat is allowed to get generated because of this electron movements from one side and the detaching and attaching of the lithium into the metal oxide creates heat energy. So this heat energy is allowed to get transferred to the electrolyte, and this electrolyte would be in most often case as a paste-like structure. Thereby, the heat absorbed because of this paste would get liberate, and slowly its phase is allowed to get changed. Because of this phase change, and small internal pressure is built within the cell. So this pressure buildup must be released to the environment. If it is not allowed to get released to the environment, what actually happens is the cell would get bulged. So you maybe you might have used different type of cell phones at the earlier time scale. That is like Nokia 1100 or the previous models. In that particular case, in the rear side of your battery, you might have used nickel cadmium batteries. So after a shorter time scale of usage of this nickel cadmium batteries, you might have faced battery bulging issues. So in earlier time scale, the battery would get bulge like this. So slowly the mixture in between or the paste-like electrolyte in between would get vaporized and get converted into the next phase, and it create pressure on the external side. So thereby you are not able to properly place the battery inside your cell phone and lock it. So that was an issue in the earlier time scale, but now all the batteries are inbuilt. So Most of the mobile phones doesn't give you the option to replace the batteries by yourself. So this is close towards the battery recycling process. So that is an entirely a different view. This battery bulging issue is not faced by this in this generation, particularly on lithium-ion cells. But this issue was available in earlier time scale, maybe 10 to 15 years back, where particularly in our locality, the Nokia and the Sony mobiles were majorly used. That will have batteries on the rear side, and after a shorter time scale, you won't be able to place the battery casing cover properly. So people used to use different techniques to place the battery within it. They make use of uh, rubber bands and sellotapes to place the battery within the entire case. So this in general create an high pressure inside it, and in that case you need to have a small vent or a small hole within it, and this vent would get busted and the pressure would get normalized. So that what takes about the safety vent, and you have different structures for it and what is the pressure that is applied and at what time the vent is allowed to get open. So there are a number of processes that you can be studied with related to it. And this is the solid electrolyte interface. So this one is your electrolyte on or the outer side of the electrolyte. You can see the dendritic growth. So this dendritic growth is the SEA layer, and this additionally acts as a barrier for the movement of electron in the horizontal direction. And next one is the heat retardant electrolyte or the separators. So here you can see the separators that is coated with the heat retardant materials or the coatings. So they will try to understand after it is getting to get ignited at what time it takes to get it completely melted, or how the flame is getting propagated to the nearby structures. So that can be understood using different photographic techniques and the thermal analysis to try to understand what would happen within the cell structure if the heat generation is allowed to get higher. And in thermal runaway process, the heat releasing reaction will lead to a battery temperature increase and gas accumulation, and the battery will cause the internal pressure to increase drastically. So that is one critical issue that deals with the battery in general. And we need to try to understand two primary concerns. What would be the scenario when the temperature is low, and what would be the scenario at the temperature is high. Let us start with low temperature condition, and this particular image present you the series hybrid drivetrain structure, where we will start with the internal combustion engine, and the output of your internal combustion engine is connected with an intelligence mode generator, and this generator produces electrical energy, and with the aid of the power electronics, the electrical energy is supplied to your traction motor, and this traction motor is coupled with a differential unit where a bevel gear is set up, and this bevel gear setup was used to propel your vehicle in an effective way. So this is a typical power flow of a series hybrid drivetrain, and here it clearly make you to understand the mechanical connection and the electrical connection. In this case, you have an battery pack in addition to deal with the power fluctuation and store the excess power that is allowed to get produced. And the typical operating temperature range for the lithium-ion battery stays close between 15 to 35 degrees Celsius. So this is the typical operating range that is preferred. But lithium and battery is able to operate from 0 degrees Celsius to 60 degrees Celsius. So that is the wider width that can be operated. But to get a proper effective output, it is preferred to operate in the window between 15 to 35 or 40 degrees Celsius. But when you look into it, let us assume the vehicle is in an entirely the cold condition. When you talk about the Lithuania, we can feel temperature close to -5 degrees Celsius, 0 degrees Celsius, or even 2-3 degrees Celsius. So the atmosphere ambient temperature is very less, and close to that, the battery pack would be enclosed and sealed. But even though let us assume the battery pack is 10 degrees Celsius or 5 degrees Celsius, that is a major issue. We'll try to understand what would actually happens when this very low temperature is available in your vehicle. So when you are trying to operate your battery at 60 degrees Celsius, at 60 or 40 degrees Celsius, the electron that is moving in the outermost part is able to move at a very good or the nominal speed. That says that the resistance would be very minimal. But as the temperature is allowed to keep on get reduced, slowly the resistance is allowed to get higher. When you look more detail into it, at 40 degrees Celsius, the resistance is very minimal. But as the temperature falls close to 0 degrees Celsius, or if even higher, assuming -10 degrees Celsius, the resistance is closely twice what actually happens at 10 degrees Celsius. And it gets even higher as the temperature is allowed to get lower. So as the temperature is allowed to get lower, the electrons movement is highly restricted. So thereby the resistance is highly restricted. When you look in controversy or in parallel with this resistance and the capacity of your battery, as the temperature is higher, the capacity of your battery lies close to 3.2 to 4 volt in general. But as the temperature is allowed to get slowly get decreased, the capacity of your battery is also allowed to get reduced. This is because as the lithium moves in the horizontal direction, it sticks over on the graphite area and doesn't get back to its original position. This is what mentioned as lithium plating. The lithium is allowed to get plated on different surface based on its movement from one location to other location, and it forms a plate-like structure or a coating layer on the zone it is allowed to get travel, and it doesn't get back to its original portion because the primary working medium for the lithium and battery is lithium. So the lithium must get back to its original portion and get settled within the metal oxide. So that must happen on every charging and discharging cycle. If that doesn't happen, it would result in the capacity fade in general. And what would happen when you try to operate at two different temperature ranges, what I have mentioned over here. So when you look detail into it, when you're trying to operate at -20 degrees Celsius and at a higher temperature of 15 to 35 or 40 degrees Celsius, this is a significant shorter where the comparable study shows that the similar battery is capable to reach close to 2000 cycles, but now it is good to 5000 to 7000 cycles as of now for an effective battery operation. Before its end of life, stating that the entire cell voltage in total should not be less than 80% when cycled at 40 degrees Celsius. But when you try to operate the same system at -20 degree Celsius, the end of life would come in just 90 to 140 cycles. So try to understand the difference. In just 90 to 140 cycles means when you try to charge your battery for 90 times or 100 times, your battery would allow to be get dead. But whereas when you try to operate your battery ambient or the battery surface temperature close to 40 degrees Celsius, you can charge and discharge your battery for 2000 times. So think where is 100 and where is 2000. So there is entirely a great scaling difference between these two. So thereby we need to try to understand that the battery operating temperature is a key factor when you deal with it. And this is for the low temperature condition. Due to high anode polarization at low temperature, the metallic lithium is deposited on the surface of the anode or whatever the pathway that lithium travels within your cell. So it will travel from one side and it won't get back to its original state. It will get stick on the different paths that it generally travel. So this is for the low temperature case, and we will look detail into what would happen for the high temperature case. As I said earlier, the optimum temperature range is 15 to 35 or 40 degrees Celsius. But in general, you can try to operate your lithium ion battery from 0 to 60 or 65 degrees Celsius. You can try, lithium ion battery is able to work on this window effectively, no issues. But it is always preferred to do it in this particular case. We have already seen what would happen when we fall below 30 or 15 or 20 degrees Celsius. Now we will look into what would happen when you try to operate above 40 degrees Celsius. When you cross this 80 degrees Celsius to 100 degrees Celsius mark, the solid electrolyte interface layer that is formed on the outer side of your electrolyte would start to get decomposed. So make it clear, you should not allow the electron to move in the horizontal direction at any point of time. When you try to open the pathway for electron to move in the horizontal direction, it would directly result in short circuiting. What actually happens in all the high temperature condition is that you will always try to create a pathway for the movement of electron in the horizontal direction. This solid electrolyte interface layer is a strong barrier to repel the movement of electron in the horizontal direction. But after the entire battery pack or the cell temperature is close to 85 to 120 degrees Celsius, it decomposes solid electrolyte interface layer. So slowly what actually happens is it opens the pathway for electron movement in the horizontal direction. And next is that at 120 degrees Celsius, when the temperature is raised to 120 degrees Celsius, the graphite anode reacts with the electrolyte. So the graphite is nothing but the swimming pool. What based on the previous analogy that we have discussed, the students will, the mischievous student and his friend will come and play in the swimming pool and they get back to their original position. Here, the swimming pool or the water doesn't react with the entire chemical process. So graphite is just a storage space where you can try to accommodate the lithium and the electron and try to get interacted with each other. And once they get back to the original position, they will try to combine in the opposite side only. But if the temperature rise above 120 degrees Celsius, the lithium would start to get react with the electrolyte. For an assumption, if the temperature is 120 or higher degrees Celsius, the water in the swimming pool will get evaporated. Similar to the previous case over here. At 120 degrees Celsius, the graphite anode will react with the electrolyte and it opens the pathway for the electron in the horizontal direction, because you will start to lose the electrolyte in between. So this electrolyte is also an electron repellent. And at 130 degrees Celsius, the separators start to melt. So in between the electrolyte layer, you will have a separator, which is also an electron repellent barrier. And at 140, the electrolyte volatilization would happen. And after 150 or 265 degrees Celsius, the lithium and the metal oxide would get a clash. So the lithium and metal oxide is that the faculty is allowed to get heated up. He is more angry. So what he will try to do is he will scold the student and the student will run away from him. So the faculty itself, himself is not too cool. He is at a higher elevated temperature. So he won't handle the students in an effective way. So that what happens at a very high temperature of 150 or 200 or even above, and in general at 200 degrees Celsius, the entire electrolyte will get evaporated and all put together. You are just opening the entire pathway for the flow of electrons in the horizontal direction. So this what happens in case of electron movement in the horizontal direction, particularly on the high temperature condition. And we have two more major breakthrough in this particular case. One is the cyclic aging, and next one is the calendar aging. So in case of cyclic aging, happens when the battery is cycled through the process of charging and discharging. So when you try to charge and discharge in a regular time scale, and the temperature that the charging and discharging happens, and its interaction talks about the cyclic aging. So for an example, let us assume when you try to charge your battery and discharge your battery at 60 degrees Celsius, the capacity of the battery drops from to 80 percentage and 34 percentage on the 70th cycle and 140th cycle respectively, compared with the capacity loss of only 4 percentage on the 140 cycles at room temperature. So when you try to operate at 20 degrees Celsius or 30 degrees Celsius, only 4 percentage of drop happens after 150 or 200 cycles. But you should not move above the extended limit of 60 or even above, and even 60 is considered as an highly alarming situation where you need to work on the cooling of your battery. And in terms of calendar aging is defined as the performance loss that happens when you store your battery without any use. You're just keeping your cell phone idle for next 15 days, for next 20 days, and at different temperature zones. And try to understand how this different temperature affects the performance loss of your battery. Talks about the calendar aging in detail. So this is the effect of temperature on the battery performance, focusing on the high temperature case. And you need to understand one thing in detail. In majority of cases, the batteries are placed on the bottom surface of your entire vehicle, and now people are trying to make use of cylindrical shaped batteries, which deals with AAA size or very small in general, and you will have close to 3,000 to 6,000 cells under your footrest. It is not that the entire battery would get busted, in that only one particular cell might get fire. So if you are able to pinpoint that particular cell and try to suppress it, the fire progress can be effectively suppressed, and you can just alert the drivers on the co-passenger to get off this entire situation. So it might be happen because of any one of the issue that is mentioned above. So this is what the high temperature case talking about. And talking about the chemistries of battery, lithium ion battery chemistries are so simple. So in majority of cases, people are not working more on the electrolyte. People are not working more on the graphite side. That is, people are not working more on the based on our analogy. They are not working more on the wall in between or the swimming pool area. So this is the graphite, and this is the electrolyte and the separator. The classification lies between the faculty and the student. So this is faculty one and the student one. This is the next faculty and the next student. So majority of chemistry variation lies on the lithium and the metal oxide. So the lithium would be placed inside a metal oxide. In this case, it is manganese oxide, and in this case it is lithium iron phosphate, and this is lithium cobalt oxide, and this is lithium nickel cobalt aluminum oxide, and this is lithium manganese cobalt oxides. So in all the cases, only the faculty and students are getting changed, and majority of cases the metal oxide uh, is equally costly as of the lithium ion battery. So that is how the chemistry of lithium ion batteries lie, and n number of studies are conducted on the chemistry perspective. So in case of the chemistry as a perspective, people have worked on the cost of your battery, the safety concern, the lifespan, the performance, specific power and specific energy. And in general, people are majority making use of lithium iron phosphates and NCA in a major role. So this give you the overall the battery progress starting from the earlier time scale to as of now. In the initial time scale, people were making use of lead acid battery as a primary energy source, and slowly in the next era, people have started to make use of nickel cadmium and nickel metal hydroxide. So nickel cadmium is what we, as discussed earlier, people were using it on earlier cell phones like Nokia and the Sony, and slowly the invention of lithium comes into picture. When lithium comes into picture, the more stable component or the less heat generation component, or when you just deal lithium with iron phosphate and lithium with nickel as a primary source, and the less heat part is when you try to increase the nickel base percentage as a variable. So slowly the power generation and the weight is allowed to get varied. So this is the entire chemistry progress of the lithium cell in detail. And when you look into how these batteries are placed within your footrest, it starts with the cell where you have the cathode part, the separated part, and the anode part. So that is nothing but the faculty and the student, the wall in between, and the graphite. That is nothing but the swimming pool. This cell is allowed to get combined together to call it as a battery, and this battery or connected either in strips using a module. These modules are placed within your pack with series and parallel connection, and they would be coined with an aid of a BMS, and this BMS in combined battery packs in different numbers would call as the battery system. So the basic cell chemistry and the basic cell voltage level, a stack of 10 cells or 20 cells, and many batteries in parallel and the series configuration coined as a battery and the module, and several modules make one particular voltage pack. So that is maybe not 400 volt, maybe 160 volt in general, and the 60 volts in a number of configuration will combine together as the battery system. So this how the battery is combined together, and hope you are all aware about what is SOC, SOH, REF, EOL, and the NOL. So the nominal capacity and the maximum available capacity that varies based on the state of health of your battery. So that is nothing but the SOH, and state of charge is what is the charge that is present remaining in your entire battery. And what are the primary health indicators of your battery? So here you can clearly see how the battery is allowed to get fire based on just a heat addition. So using a fire gun, you have a battery over here, and the heat is allowed to get passed from the external surface. So based on this heat, the electrolyte in between is getting damage, and it creates an battery bulging, and slowly the anode and cathode is getting interconnected, and it creates a heat generation within the battery. So slowly what actually happens is the battery casing is allowed to get busted, and the the smoke formation, and after the smoke formation, the flame is allowed to get propagated. So this is how a thermal runaway happens. So health indicator is an important parameter that characterizes the degree of battery aging. Direct HI is referred to the characteristic parameter that can directly represent the degree of battery aging, and indirect HI is referred to the data that need to be extracted from the charge and discharge cycle. So direct HI is what you can visually see and try to understand the health parameters or the aging impact of your battery. And for indirect, you need to derive data from the charging and discharging profile, or just taking more details from your PMS. So that what is a key point over here. Whether am I audible to you? Whether the screen is visible?
Yes, sir. Yes, sir. Yes.
Okay, sir. Okay. Thank you. And talking about the health indicators in general, the direct health indicators are nothing but the capacity and the internal resistance, and the indirect health indicators or the average discharge voltage, the maximum discharge current, the constant current of the charging time, that by the C rating comes into picture, the charge terminal voltage, and or key focus is on the change in temperature based on the change rate. Either it can be charging or discharging. We'll try to understand how the temperature is allowed to get raised within the cell and what are the primary causes for it and what would create this temperature sense. In general, we'll try to monitor with an aid of BMS the voltage, temperature, and the current of your individual cells and the number of cells, and we'll try to quantify what is the stage of charge and what is the state of health, and with that we can pinpoint what is the fault and the status of all the cells. So this is the key part of the health indicator, and now we will try to understand what is thermal runaway. So thermal runaway, based on Somino's theory, says that the heat generation by your battery must be effectively dissipated to the environment. If the heat generation and the heat dissipation is not equal, the heat would allow to be get withstand within your entire system. So if this entire system is allowed to get heated up, it would result in a thermal runaway condition. So thermal runaway condition is that the slowly heating it is allowed to get passed to the electrolyte, it is getting allowed to get evaporated, and the remaining stuffs happen. So the thermal runaway in general is an high temperature battery affective condition. So here the first curve talks about the heat removed plot, and QG is the heat generation plot, and this is the static part. So this stable part is what you need to operate your system, and when you are trying to move away of this system, what actually happens is it results in a high temperature condition. So the chemical reaction produce heat, and the gases, because of the electrochemical process, the heat speed up the reaction, producing further more heat and more gases. As because of it, an uncontrolled possible feedback mechanism comes into picture, and thereby it results in a thermal runaway. So this thermal runaway can happen because of any abusive condition. Abusive is that you are trying to intentionally hurt or physically affect or physically torture your battery. So this abusive can be either thermal, electrical, or mechanical. So because of it, it might result in a temperature rise. And as said earlier, it starts with electrolyte decomposition, electrolyte volatilization, cathode decomposition, and after all these process happens, it would result in a thermal runaway. And initial to stage 1 and stage 2 or more or less in the controllable part, but once it moves to stage 3, the hazard level is enormously higher, and the flame propagation and the heat ejection would be much more higher. When you try to understand, if you try to intentionally hurt a battery and allow it to get busted, it would create a temperature range close to 300 to 400 degrees Celsius. So handling that particular high number of temperature with high pressure is so tedious in your entire battery pack. Now we'll try to look into how the flame propagation happens in a small case condition. In this case, this particular vehicle is parked under in the underground parking of the malls or the skyscraper buildings, and in majority of developed countries, we are not allowed to park or electric vehicles in the underground. So electric vehicles are allowed to park only in the open environment. So here you have a battery pack close to 3,000 to 5,000 cells. In that, any one particular might get thermally, mechanically, or electrically abused. Because of it, it might get a temperature rise, anode cathode interconnection resulting in a short circuiting, and slowly it would result in a smoke formation, and within next few seconds the battery is allowed to get fired and the entire vehicle is allowed to get to a critical case. This happens either because of mechanical abuse or electrical abuse or thermal abuse. Mechanical abuse says that the battery is allowed to get crushed by any external sources or get penetrated by any external sources. So that way, this component is trying to connect your anode and cathode and result in a short circuiting. And next is the electrical abuse. In case of electrical abuse, either it can be an internal short circuiting or overcharge or over discharge condition. And third one is the overheating condition. The overheating condition happens because of the thermal runaway happen in one particular cell and the heat generation, and it affects the next cell. So because of high temperature from the external source would affect the cell chemistry, and thereby it would get into the thermal runaway condition. It starts with smoke, flame, and at the end of it, it would be a huge explosion. When you look more detail into the cell structure, the separator would allow to get teared, or the separator would allow to get pierced, or the separator would be allowed to get collapsed. Because of it, the thermal runaway might happen. And you can see a parallel image similar to a car, as a bus is allowed to get resulted into a thermal runaway. And when you look more detail into the time scale, it starts with close to 49 to 50 seconds, and it just takes 2 to 3 seconds for the entire battery to allow to get busted, or the entire bus to allow to get busted. So this image starts with the time scale of 48, and it runs till I think close to 58. So just the video is fast forward for 10 seconds, but within the 10 seconds, you can try to understand how fast the flame propagation happens. So when this happens in the underground, it is too hard for the firefighters to suppress the entire flame and get rid of the situation. So as I said earlier, in general, we are not allowed to park your electric vehicles in the underground parking in the highly developed countries. And what are the different mechanical abuse-based studies that can be handled? Is that the deformation of the fracture of LIB in different loading condition? So here they have given a short example of prismatic type. So this is the prismatic type battery, which would be rectangle in shape. So here they are trying to make indentation above it. So you can see the battery structure is allowed to get collapse because of this indentation. And after that, you try to charge and discharge your battery. You can try to understand how it get affected. And next one is the axial compression the elongation road. You can try to make an compressive axial compressive load over the cylinder. So this is an CT scan model of your cylindrical type cells. So where you can see the vent surface on the head of your battery. So this is the vent surface on the head of your battery. So this is the vent surface. So with this, the mixture can try to move to the atmosphere. And it is in a jelly roll structure where the anode, cathode, and the electrolyte would be converted into a sheet-like structure, and it will get wound around the cell. So that way you can effectively make use of it. And in case of mechanical system, either it can be thermally forced system or electrically forced system or mechanically forced trigger system, is that you will intentionally try to force the system, place an internal particle into it, or place a pre-hole separator, or place a phase change material because of heat addition. It would allow to get melted, or a shape memory alloy, try to understand how it happens, or an electrically interacted or internal particle that is present within the cell. And when you try to charge and discharge it, we will try to understand how it actually works. And these are the different layouts over here. And this talks about the mechanical abuse. So in case of mechanical abuse, you externally create a force on the battery and try to understand how it get converted into a thermal renovation. So here you have an image of a prismatic type battery where you try to intentionally create and puncture in it. So because of this puncture, the anode and cathode would get interacted, and a short circuiting happens, and internal heat generation happens, and slowly the heat is allowed to get propagated, and the smoke formation, flame formation, and at the end of the day, it would get busted. So this what talks about it, and here you can clearly see what would happen if the nail is penetrated. This is the anode collector plate, the cathode collector plate, the separator in between. When I try to connect your anode and cathode, the electron tries to move in the horizontal direction, and it creates a short circuiting as present over here, and it might result in a battery fire issue. So once the nail is allowed to get penetrated, the reaction time is very minimal, and because of it, it would result in a high pressure and high temperature formation, and a flame progress is allowed to happen within the system. So this is the issue related with the battery fire. And what are the major gases that is allowed to form here is that certain traces, hydrogen, carbon monoxide, carbon dioxide in majority of cases, hydrofluoro, hydrogen chloride, hydrogen cyanide, small droplets of organic solvents, ethane, methane, and other hydrocarbon traces is also able to form because of the different materials that you use. So that is the reason why the firefighters are even now getting trained when you are just handling to suppress the battery fire issues. They should not be so closer to the battery vehicle. What velocity the water is allowed to get spilled on the vehicle, or extensive research studies that are even conducted. And looking more detailed into the electrical abuse case condition, in terms of overcharge, let us assume you are just placing your mobile phone in charge for the whole night and not picking it out of charge. What actually happens is, as I said earlier, this graphite is the swimming pool, and this is your faculty and student, and this layer is the solid electrolyte interface, and the shaded one over here is the separator. So what actually happens is, slowly the solid electrolyte layer get decomposed, and the separator get decomposed. That is, the electrolyte is allowed to get decomposed, and lithium plating happens. And after charging it above 100 or 120 or 140, the battery rupture would happen. So the vent is allowed to get open. Slowly, the thermal runaway is initiated. So this is what happens when you try to overcharge your system. But now advanced BMS is handling this part. So when you try to overcharge or over discharge, the BMS plays a key role in trying to suppress this uh, charging and discharging part. So at normal operation and over discharge from 0 to 8 or minus 10 or minus 12 or minus 20, the pathway for movement of electron in the horizontal direction is allowed to get open. And thermal abuse is that you are creating temperature on the external side and try to intentionally heat the battery and try to understand how the flame is allowed to get problems. So these are the various parts that we need to understand before trying to move in detail into the thermal runaway condition. And as you know, the term IEC and Society of Automotive Engineers, there are n number of standards that has been generated by IEC and SAE. So you can clearly see that this is an heating coil wound around the cell and trying to understand how the heat affects the cell, and introducing of mechanical dent. So you can see a dent is allowed to place over the cell, and slowly an pin or an external nail penetration. So this is the nail penetration. So we have different standards for it, and in number of studies you are conducted and try to understand how does this happens. But what is the challenge is that the standards available may not be the representation of the real world scenario. Each and every cases are entirely new. So the standards are not the representative of new real world scenario. So lack of harmonization on the testing condition, the testing parameter, the pass and fail criteria all plays a different scenario. So very different TR methods and test setups is a key point over here, and controversy on short circuiting TR testing is also resulting an issue. So the range of condition that change the severity of the response to abuse, and the testing at the component level may not be comparably or testing the same system level, and aging influence on the safety parameters are all key challenges as of now, because we have standards, but all these standards doesn't happen every time on your vehicle. So the battery is allowed to get crashed, the battery is placed inside the roof condition, the battery is getting toppled, the vehicle is getting toppled, you are charging it for a longer time, I'm not charging it for a shorter time. So it is getting differed because of the user. All of us doesn't follow the same pattern of charging, discharging, or using your mobile phones. So that creates a typical template to try to understand why a thermal runaway might happen. So the key challenges is that the mechanism for the thermal runaway is still in progress. The link between abuse and the initiation of thermal runaway and the types of abuse and the severity of the fire propagation need to be still understood. Adaptive control measure to detect the TR and the number of sensor present in the focus on the module and slowly to the pack scale is still in progress, and the academic focus on the prevention is still running on, and further effects on the detection, compartmentation, and the suppression need to be understood. So this is what the current scenario, and focusing more towards the time scale, I will give you a shorter view of one particular case study. So here we are trying to place an prismatic cell. The first one is NMC and next one is LPF. That is placed inside an heating chamber. You can see the cell is placed over here and enclosed to a greater extent, and it is coupled inside a heating element. So this has a heating element, and we are trying to heat it slowly. And as said earlier, the cells get heated up. It slowly started to get bulge. and the vent opens and the smoke is allowed to get formed, and after that the battery is allowed to get teared and the fire happens, and after a short scale an explosion is allowed to get happen. So this particular case, we are trying to incorporate the temperature and pressure and the voltage sensors and try to understand what is the pressure that is created because of it, and what is the maximum temperature that is allowed to happen, and what are the various gases that is allowed to get emitted from this particular scenario. So for this, n number of cases can be conducted and we can try to understand it. And similar, I will give you another interesting case plot is the early warning sign based on the gas production. So this is another interesting study starting from an initial peak formation to the thermal runaway occurrence. If the cell is allowed to get heated up based on a detailed analysis, a small high peak is originated, and this high peak origination can be identified as a thermal runaway indicator. So after this high peak, it takes a shorter time scale to completely get fired. So this can be quantified based on incorporation of an pressure sensor or gas monitoring sensor within your entire battery pack, and try to understand how does this happens in general. And related to it, we have done few more works in this particular case, where the battery is allowed to place inside passive system. So this is a phase change material, and we have tried to incorporate the battery within it, and it is coupled with an cooling system where the copper coil is allowed to placed on the sides of your battery, as looks over here. So combining an active material and passive material coupled with effective additives, we have tried to understand how effectively the battery heat generation can be coupled with or suppressed with this various case studies. So this article has been published in a journal. So if required, I can share you this journal too from my end, so you can take time to read it. So nothing but we have tried to place a battery within and phase change material and try to understand at different C rating by charging and discharging it, how effectively it can be cooled in different case condition. And we have also done a simulation part study related to it, and an earlier time scale while I was here, we have deal with the publication and different Indian patents related to the hybrid thermal system based on how effectively the cooling system can be incorporated to suppress the heat generation. And we have also done a few in-house projects and tried to understand and quantify the state of health, state of charge, and the end of life of your battery with an aid of the data acquisition system, and pulled in IoT and AI stuffs to predict the temperature rise, battery surface temperature, battery core temperature, the thermal runaway triggering initiation, and alerting the drivers and the co-passengers to get rid of the situation. We are working on this similar steps to try to understand or couple the in chemistry detail and the temperature rise in connection with the battery aging and the usage of your battery. And the next interesting part that we are working on is the multimodal deep learning for early thermal runaway prediction and propagation with the aid of barrier suppression. So this what is the study that we are talking about initially, mechanical, electrical, and thermal abuse. It is not that the entire battery would get affected. One cell slowly get heated up and it is getting converted into flame and the flame propagates to the nearby zone. So we are working on a thermal barrier or a super absorbent material that can be placed around your battery or placed in between the battery modules. So thereby it can effectively suppress the heat generation and it can safeguard you from different scenarios. So we have done a large number of studies related to it. So this is the battery pack, and we try to intentionally abuse the battery and try to understand how the heat is allowed to get generation with the aid of a thermal camera, a heat gun, and a high-speed camera. It looks more similar to this. And we have quantified what is the voltage, what is the depth of penetration, temperature rise, and based on the data available, coupling with the AI techniques, we are trying to understand the triggering point and the time for the flame propagation in the remaining source. So this is also one interesting study that we are working on. You can clearly see here over here. So this is how the nail is penetrated within the cell, and this is the result of post-mortem study. We have entirely cut the cell and try to understand how it affects the internal structure of your cell, and with an aid of FLIR cameras and the thermal high-speed images capturing, we have break down it and try to understand what happens in phase by phase, and try to understand it. And this is an example of, I don't know whether it is playing. Sorry for it. This is an example of study over here. Okay, yeah. So when you try to puncture it, it creates a huge amount of flame source, and this flame source is captured in a very slow pace and try to understand at what is the maximum temperature the cell is allowed to get heated up, and how this heat is propagated to the nearby cell or the neighboring cell, and we will try to understand how it can be effectively suppressed. So that is the key point over here. So you can look in detail how fast one particular single cell, this is not the entire battery pack. This is a real-time experimental study that we have conducted. How fast the flame propagation happens and what is the maximum temperature rise, and how effectively it can be suppressed to getting propagated to the nearby cells is all the different works that we are currently working on. And these are the other remaining projects that we work with. So I think within the time frame, I have given you some interesting idea about battery, fire issue, battery thermal runaway, and few of our research works that is we are currently working on. And with this, I will try to conclude my session. And now the part is open for the participants. If you have any interesting queries related to it, I'm happy to address it. Thank you.
Thank you, sir. It was really a wonderful presentation with good illustrations. Dear participants, any questions? Dear participants, any questions? Anyhow, thank you, sir. It was really a wonderful presentation. Thank you very much.
Okay, sir. Thank you. Thank you.
Thank you, sir. And dear participants, tomorrow again the session starts at 6 p.m. Have a great day. Thank you.